Welcome everybody, Mr. Dean here. Today we're talking about the second derivative test, and we're trying to put it into action by figuring out how the second derivative test works alongside the first derivative test. It helps you tell where the minimums and the maximums are in a graph and how it has to do with concavity and the points of inflection. We're going to wrap that all into one example. Let's see how it goes. Our function that we're looking at is e to the x times x cubed, and it's within this domain, this closed interval of -5 to 2. Now remember, the extreme value theorem says that every function that is differentiable along a closed interval does have an absolute minimum and maximum. So that is a guarantee, and we're going to use the first derivative test to figure that out. So first derivative of e to the x cubed, the way I thought of it was as two products, right? We use the product rule, or one product, two terms, and I found the derivative of the first one times the regular old second one, and then the regular old first one times the derivative of the second one, and I set that equal to 0. And what I got, I realized that I could factor out an e to the x, and I could factor out an x squared out of each of those terms and set it equal to 0. And from there, I figured out that, well, if the zero product property would tell me either this product or this is equal to 0. So clearly this is 0 when x equals -3. We solved that. But when is this equal to 0? Well, e to the x is never equal to 0. All right? But x squared, of course, is equal to 0 when x equals 0. So we have a little head start, or a start on our critical numbers, 0 and -3. And each of those I plugged back into the y, into the f of x, and I found out the coordinates there. The extreme value theorem says I also want to be sure to check my endpoints, right? -5 and 2. And so I checked those, I put those back into the function, and I found out what those coordinates were too. So I kept a list on the side here. All right, now I'm not 100% sure that those are guaranteed to be absolute minimums, local minimums, or whatever. So it's time to look at the second derivative and see what that has to do and how that helps us. Now the second derivative, I'm taking the derivative, of the first derivative. All right, so I'm taking the derivative of this function here. All right, so the very first thing I did was take the derivative of the first one, plain second one. It's kind of the product rule in action once more. Be very careful. And I ended up with 4 terms. They look like that. All right. Let's take a look down here. So work those out yourself. We did those very fast. But my next step is to factor out e to the x. They all have e to the x in common, and they all have an x. So when I factor that out of each one, this term's missing an x squared. This term is missing a 3x. This third term is the same as the second term, and this one's missing just a 6 when I factor out an e to the x times x. So let me bring this together a little bit. So we have e to the x times x squared plus 6x plus 6. And I want to set that equal to 0. The second derivative test, when we set it equal to 0, that'll find our points of inflection. And we'll use it to find whether where the graph is concave up and concave down. But don't want to get ahead of myself. I need to solve this. Once again, this tells me that x is 0. And this part here, it's not factorable, but I used the quadratic formula and save you some time. I'm not going to go through the quadratic formula, but I found that the x's were there. And I'm going to put those into decimals. So I had -4.7, somewhere around there, and I had -1.3, and I had a 0. All right? These are possible points of inflection, not guaranteed. There are a list of possible points of inflection. Points of inflection are, again, where the second derivative is 0, or in other words, where it's concave up to concave down, or changes from concave down to concave up. We could take a look at it on a graph in just a bit. So we're very interested in these points for our second derivative, and those points up there for our first derivative. We're going to go to our sine graph. We're going to use both of them. I'm going to use first derivative and second derivative. So here it goes. The top derivative you can see there, I put in -5, that was my endpoint, and I put in 2 for my endpoint. I suppose I could have used 2 and a -5 for endpoints here. Not all graphs have restricted domains, but we'll work within what we got. And let's see here. I'm going to put in my first derivative. This is my first derivative graph. It's going to tell me the slope, right? First derivative is slope. I'm going to put in -4. I'm going to put a number between -3 and 0, like -1, and I'm going to put in a 1. And I plug each of those into my first derivative. Plug those into my first derivative function. And I just need to keep track of whether it's positive or negative. So in between here, it's negative. In between here, it was positive. And after 0, anything positive got me a positive slope. All right? And what that is telling me is literally the slope goes down until -3, and then the slope goes up the whole rest of the way. So I've just discovered that -3 must be a minimum, right? It's an absolute minimum. Let's look at the second derivative and figure out what that does. I plugged in points into my second derivative. I already did this. I plugged those in and I got it's positive and then negative and then positive. So what that tells me is positive second derivatives tell me that the graph is concave up, and then all of a sudden it goes concave down, up like a cup and down like a frown, and then up the last bit from 0 to 2. All right? Now that tells me that 0 is a point of inflection because it changes concavity. Same with -1, also a point of inflection. But look at this, -4.7, it's concave up all the way through. There's actually nothing special about -4.7. It is not a point of inflection. Again, it was on that list, but not guaranteed to be a point of inflection. All right, so let's gather our thoughts. Let's try to make perhaps a graph a little bit here. We'll get a thinner graph. Let's see here, something like this. It's going to go from -5 to 2. And it won't be the cleanest graph of all time. It won't be necessarily the scale. We'll get down here to -2, but it'll give us the idea of what's going on. All right, so remember that we had a minimum at -3, and it was -3 was at about -1.3. It was right about here. So there's our minimum. And we're going to use this idea of concavity. So in between -5 and -1.3 on our x-axis, we're going to go, -5 was about -1, we're going to be concave up. And then at -1.3, which is right around there, it's going to change concavity. Change. We're at a point of inflection, and it's going to be concave down until 0. So I need to change to be concave down. See that? I wanted to go right through 0, 0. I almost made it. And then past 0, it's concave up again. And remember that 2 gave us 59.1. So way up here, there's like a break. Way up there is 59. And it's going to be concave up, of course, like that. Way up there, way past that. So it's a little sloppy, but we actually have a pretty decent look at the graph. There's not a lot going on. We have a minimum here at -3. We have a maximum way out here. And we don't have any local mins or maxes. Not all graphs are like this. This is an interesting one. All right. A point of inflection again right there, and a point of inflection right about here, where the second derivative is 0. The second derivative is 0, all right? Now let's take a look at the actual graph. Let's take a look at the Desmos version of this graph and see if we got anything right. Moving on over, this graph is more spread out in the x direction, but not bad. Pretty good, -5, here we are. Now it's an endpoint. Now at an endpoint, you could have extrema. You can have either a global max or a global min. But what you cannot have at endpoints is local mins or maxes. And it kind of looks like this would be a local maximum. It's the biggest on this side. But because it's cut off, we can't see what's on the left side. most calculus people use the definition of local max, and they say, well, that doesn't satisfy local max. So with this point here is not, of course, an extreme. Extreme is not a global minimax. It can't be a local minimax. So it's basically just sitting there. It's nothing. This, however, is your absolute minimum. There you see our point of inflection. We had figured out it was exactly negative, well, 1.3. It was rounded. And then we have a point of inflection at exactly 0. And then way, just trust me, way up there at 259.1 was our max. So not a bad looking graph. We didn't do too bad. Hopefully that makes some sense to you, and it wasn't too painful. You got to see why we use the second derivative, what the point of inflections are all about, and how that helps us make a graph. That's all we got here from our home quarters at South Deerfield, and hope to see you in class soon.